Hi all, my name is Moussa. I'm associate professor at University of Qatar. So I present scalable analytics of air quality budget with Apache Spark and Apache Sedona. This paper was submitted to DEBS 2021 Grand Challenge track. We all know that air pollution affects human and animal health and earth ecosystem badly. It pollutes lakes and soils. So that we need to sense the air quality. We need also to analyze the collected data because it's big, and we need for that efficient algorithm to query the data as well as big data frameworks. That in order, of course, to make the right decision. The outline of my presentation is the following. I invite you to check the 2021 contest video, which describes the contest. I will present my solution overview and as well as the design and implementation details of query number 1 and query number 2 in my solution. Query number 1 is calculates top K cities with year-to-year comparison of AQI, and Q2 calculates the longest treks for each city. Finally, I will conclude my presentation and present future work. My solution is based on open source framework, namely Apache Spark and Apache Sedona. Apache Spark allows in-memory processing across a cluster of machines, as you notice here. It's fault tolerant if one node's phase the failed tasks are distributed across the other nodes. And it's also highly scalable. We can add workers with no downtime. Apache Sedona implements special operations, namely like the reverse join coding, special join, and also it allows to create special indexes over large-scale special data. For my solution, I used Spark SQL and dataset rows for Q1 and active cities tracking, and I used workflows and Java pair RDDs for query number 2. So each batch includes current year measurements and previous year measurements and the batch size. Each measurement is described by timestamp, which is the event time, and also some information on the location of the measurements, latitude and longitude, and two measures, particulate matter 2.5 and particulate matter 10. The text in orange shows attributes that we need to calculate. Namely ingestion timestamp for tracking active cities, as well as the city for solving Q1 and Q2, AQI 2.5 and AQI 10, respectively calculated from particulate matter 2.5 and particulate matter 10 measures. And also we need to assess the quality of the particulate matter measures, whether they are good or not, with a Boolean value for calculating the tracks in query number 2. RDDs and dataset rows, they are distributed across the cluster for the batch. German spatial shapes with 8,000 polygons and more is replicated in all the cluster. Active cities last time stamps, current year AQI summary, previous year AQI summary, and city sex summaries are distributed across the cluster. Now I will present Q1, which calculates the top key cities with respect to yearly AQI improvements. So first we receive the batch. Second, we timestamp the batch with an ingestion TS. And third, we perform the reverse geo coding using Apache Sedona Spatial Join. And fourth, we refresh the city last timestamps in order to track active cities. And fifth, we calculate the AQI calculus with respect to the specification in the context. So we calculate the average, the sum, the count of each pollutant. We calculate the max AQI for each city. We rank active cities, and finally we select the top 50. And we also calculate summaries over batches, namely current year summary and previous year summary, in order to perform Q1 on snapshots. For active cities tracking, we have 3 cases. So the first case, we have a new city data, so no match for the city in the city's last timestamp. For that, we need to add an entry for that city with the batch ingestion TS. For the second case, a match exists, so we need to update the timestamp of entry city I and set the last TS to the batch ingestion TS. And finally, for the third case, no match exists for the city in the received batch, so the TS of the entry of the city remains unchanged. As I mentioned earlier, I used Apache Spark SQL for Q1 and active city tracking. Here, an example of algebraic expression for active city tracking. So first of all, I perform projection of current year batch measurements on city and the timestamp. And I perform a union all with city's last timestamps. Then we group by city and calculate the max. The star entries here in that example correspond to cities like Mainz, Magdeburg, and Langenau, which are either new entries or were updated. They've got the batch ingestion TS as last TS. Whereas the Clover here, these two entries, Clover entries, corresponds to cities like Letzwigsfeld and Berlin, which kept unchanged their last TS, so known measurements in the received batch correspond to these two cities. In this slide, I show screenshots of Q1. So here we have the top 20 of cities. And here we have the current year API summary with city and date and the sum of pollutants measures, as well as the count of measures. Query number 2 is more complex than query number 1. And it calculates the longest tracks. A track is defined as a time duration during which a city has good quality index. It's described by a start TS and an end TS. And of course, we calculate the duration of each track. So city track summary stores best track for each city. And for each city, we have this entry, a best track and the last track. The best track is the average received to compare with future tracks. And the last track might be merged with the next track if they are sequential in time. That's why we save it. The first step in the workflow is that we need to compute the batch track summary per city. Each new batch triggers the refresh of city track summaries. We need to group by city. And for each city, we summarize all measurements as follows. We calculate the first track to merge with the last track. We calculate the middle best track to compare with the best track. And we calculate the last track to merge with the upcoming first track. And we also describe the pattern of the 3 tracks using a pattern identifier to simplify the processing. The second step in the workflow is to refresh, of course, city track summaries. So once we have the track summaries over batches, the old one, and the track summaries for the current batch, we perform a full outer join on city. In next slide, I saw some patterns. So here, pattern number 0, all good here, good values are false. So first track, best, middle track, and last track are, of course, null. While the last one, we notice that the first track is not null, the best middle track is not null, and the last track is not null. So we have, if we have n measurements for a city, these n measurements will be summarized by 3 tracks, and each pattern have 1 ID. In total, we have 8 patterns. So the first case is that no match for the city in the batch track summaries. It means that the right-hand part resulting from the outer full join is null. So the city will keep its recorded best track and its recorded last track. The second case, no match for the city in the track summaries over batches. This means we have new city data. So the left-hand part here is null. In that case, we use the batch track summary per city to calculate the new entry for that city. The first track and the middle best track we select the best of them and we assign it to the best track, and the last track is assigned to the last track. In the third case, a match on city exists. So for instance, for pattern 6 and 7, we first proceed with merge of last check and first check. Then we calculate the best of the two, and then we calculate the best of the best track and the best calculated here in order to assign it to the best track for that city. And the last track is assigned to the last track of this city. The third step in the workflow is to compute the longest track for each active city. For that purpose, we need to select the active cities as follows. We calculate them. Either they satisfy that last TS is greater or equal to batch ingestion TS minus 10 minutes, for instance, and we perform a join with city track summaries. Then we calculate the longest track of each active city. So HW denotes the histogram window. It's the current batch ingestion TS minus the first batch ingestion TS. So the final step is to build the histogram. So first we have to count the number of cities for each bucket. We count it as follows. If the track duration SI of city I is in that range, we'll add +1 to bucket J count cities. And finally, once all counts calculated, we divide each count by the total number of active cities to calculate the percent. In that slide, I show some screenshots of Q2. So we obtain a histogram summarizing what happened from the first to the current batch. For instance, from the first batch to the fifth, from the first to the 22nd batch. In conclusion, we proposed a solution for Q1 and Q2 based on open source frameworks. It's the workflow is highly optimized. It performs parallel processing, and all data is distributed on the cluster. Preliminary evaluation allowed us to evaluate our solution. We performed 22 batches on the virtual machine with 16 gigabytes. We note some limitation in Spark. RGDs are immutable, so we need to refresh through calculation, and this will create some burden at the RAM. As future work, we would like to conduct more performance analysis on a cluster utility using Apache Sedona spatial indexes, comparing the different settings like R3s and quad trees, for instance, and also do different setups of Spark cluster. For Strect calculus, what we propose is that for each city, the N measurements are summarized into a triplet. We would like to investigate approximate approach where timestamps close in time have high chance to relate to the same air quality and no need to calculate these 3 secs to summarize the N measurements of each city. And also for spatial analysis on historical and real-time data, both queries Q1 and Q2 perform analysis per city. Cities have different population, different area, different census coverage, and also may include parks and industrial sites. Consequently, we cannot aggregate by city. We propose to either use Uber H3 or GeoHash indexes to adjust the zone dimension within the same city. Or also we can use high-low clustering or spatial autocorrelation to perform spatial analysis on the data. Thank you for your attention.